real title.
Good evening, Earth. This is Adam Sturch broadcasting from the Mushroom Mansion, Taos, New Mexico, working on oil painting orange.
What it really should be called is
Yes, second in the secondary triptych. Okay, this is pretty set up. The next big step will be a complete glaze of the entire surface area, probably with an alizarin crimson, and then working into it with some yellows. But before I do that, I want to redefine the forms that are present already with some just yellow and alizarin crimson light. Or I think it might just be alizarin something. The next step down from deep. But anyway, it's something medium red, and work the forms with sort of a circular blending swirlish brushstroke motion with a long slender brush and then this fat brush to lay down the initial base coat of red. So work on that. Here we go.
What the difference is. I guess so. The reason I started out with this illustration, which is from the book Parallel Botany, if any of you know that book. It's a charming little book, and it talks about a completely hypothetical, completely fictitious plant kingdom. It's basically a book of anatomy for a bunch of plants that never existed, at least not on this planet. But I put this up here to illustrate the point that even though plants and animals have an extreme relationship of interdependence with each other, plants are not at all like people, and they're not at all really like animals, even though we as part of the animal kingdom and the rest of the biosphere really depends on plants. For one thing, plants by and large don't move around. They are stuck in one place. And so in order to develop evolutionary strategies for protecting themselves, getting along in the world, they have tended to evolve biosynthetic strategies as opposed to behavioral strategies. In fact, one famous botanist, Tony Swain, put it very succinctly. He said, plants have substituted biosynthesis for behavior. And if you think about it, that's an interesting concept. Plants are chemical virtuosos. A greater variety and a greater number of complex organic molecules are found in the plant kingdom than have ever been synthesized by all the organic chemists since the beginning of time. Plants outstrip them in terms of varieties of different types of compounds. And the reason that plants are able to do this, one of the main contributing factors and a kind of neat trick that plants can do that's unique to the plant kingdom is that plants are photosynthetic. I put this up here. This is a rendering of the cosmic ayahuasca by a Brazilian artist. I put it up here to suggest the idea of photosynthesis. Actually, I guess I could have put an electron micrograph with a chloroplast or something. But this seemed more appropriate. Plants have this ability to take simple elements, carbon dioxide, water, sunlight, and transform them through the process of photosynthesis into complex organic molecules. The molecules of life, sugars, lipids, amino acids, nucleic acids, all these things basically proceed through the process of photosynthesis. All other organisms in the biosphere are essentially parasites on the plant kingdom. Because, well, not all. I mean, you want to be careful about using those kinds of terms. But most organisms in the biosphere are heterotrophs. That means they don't make their own nutrients. They don't make their own sustenance. Plants are autotrophs. They can, out of sunlight and water and carbon dioxide, manufacture their own food. And that's what the process of photosynthesis is. As energy impinges on the biosphere from outer space, the plants, through chlorophyll, are the first to grab that energy and do something with it. And then from that point, as this electromagnetic energy becomes transformed into chemical energy, it basically cascades through the entire biosphere. Everything else feeds off the plants, but the plants are what is able to fix that energy into the simple sugars. It's a busy slide, and it's probably not visible to most of you, but that's probably just as well. You won't know in the but this is one of the things that plants can do as a result of their photosynthetic ability. Not only can they make the major molecules of life that we talked about, the sugars, the proteins, the amino acids, all these things that are basically universally distributed in all the organisms and on which we depend for life. These we call primary metabolites. Primary because they're universally distributed and they're pretty much essential for life. But plants, in addition to that, can make a vast array of what is sometimes kind of pejoratively called secondary metabolites. And that is, these are the chemical compounds that make plants interesting, that make them these chemical virtuosos. Plants have energy to burn, so because of their photosynthetic ability. So there are no constraints on their energy. They can use that energy and they can seemingly waste it. And for a long time it was thought that these secondary plant metabolites, which are things like alkaloids, terpenoids, your essential oils, your tannins, these sorts of things, are all these plant secondary metabolites. And it was thought that they were secondary because it wasn't really understood what their purpose was. They just thought that they were some kind of metabolic waste product, basically, just a physiological garbage that the plant made and sequestered in its different parts. And what has come to be understood probably in the last 10 to 15 years, maybe the last 20 years, is that these so-called secondary metabolites, this vast array of structural diversity that plants have evolved, are not really secondary at all. The purpose that they serve the plant is to mediate the relationship between the plant and the rest of its environment, between the other organisms in its environment. From other plants to microorganisms to fungi to grazing animals and also humans, because we're also organisms in the environment that interact with plants on this molecular level via this molecular language, if you will, that plants have evolved. What this slide illustrates is basically two things. It shows the primary gateway for energy and simple compounds to get into primary metabolism in the plant. That's CO2, water, plus light energy. And that feeds first into the pentose phosphate cycle, where you get your simple sugars being created, ribulose diphosphate. And then, these are black boxes, you understand. There's a lot more going on here than is implied. You get first your simple sugars. That leads eventually down the spine of primary metabolism into your tricarboxylic acid cycle, and thence on into your amino acids, which lead eventually to proteins, and also your lipids come out of the tricarboxylic acid cycle. This is sort of the spine of primary metabolism. What's perhaps more interesting is that at different branches along the spine, you get things coming out that lead into the major classes of secondary metabolites. For example, coming off the pentose phosphate cycle from the simple sugars, this compound called shikimic acid. And that's your first aromatic compound. Aromatic in the sense, not that it smells good, but aromatic in the sense that chemists use, or that it is a precursor to compounds that contain benzene ring, an aromatic ring. And from shikimate, you get the aromatic amino acids formed, the three essential amino acids, phenylalanine, tyrosine, and tryptophan. And from those, you get a vast array of secondary compounds, the ones that we tend to be most interested in as psychopharmacologists are the aromatic alkaloids. An alkaloid, by the way, for those of you that don't already know, is a plant secondary compound, if you will, use a pejorative term again, but a plant metabolite that's not part of primary metabolism that contains nitrogen. You can sort of define an alkaloid obviously by what it is and what it is, but one of the essential requirements is that alkaloids contain nitrogen. So the aromatic amino acids lead to the aromatic alkaloids, which include things like DMCs, psilocybin, multiple hallucinogens, also things like morphine. Many of the drugs of use and abuse that are so economically important are these aromatic alkaloids. In addition to the shikinic acid also gives rise to the phenolic compounds such as cinnamic acid, caffeic acid, where these tend to be flavorings and essential oils, flavorings and literally aromatic compounds in the sense of fragrances. This is one of the main branches of primary metabolism that leads to aromatic type compounds. Further down the chain from the Krebs cycle, you get branching out of the Krebs cycle, you get aliphatic amino acids, things like valine and lysine, that lead to another class of alkaloids, the aliphatic alkaloids, which include things like nicotine. Some of the trophates are also aliphatic. Pyrrolysidine alkaloids are aliphatic. That is, they don't incorporate an aromatic ring, and they're not derived from one of these three aromatic amino acids that are so important in metabolites. But also, coming off of the Krebs cycle, is a two-carbon fragment called acetyl-CoA. And this two-carbon fragment feeds into a number of secondary product biosynthetic pathways. For one thing, it leads to both fatty acids and lipids, and a class of compounds called the acetogens, which are just many of these acetyl-CoA units joined together, and you get things like butane belong to the class of acetogens. But acetyl-CoA can also lead to metalonic acid, and metalonic acid is basically a 5-carbon unit that leads to the terpenoids. And the terpenoids are down here. You have the simple terpenes like menthol, which basically are 5 or 10 carbon units. You have the sesquiterpenes. One example is picrotoxin. And the diterpenes, you've heard this morning a lot of talk about salvinorin, and that's a classic example of a diterpene. And even more complex terpenes such as digitonin and other steroid-related compounds. So these are all basically built up of many units of metalonic acid joined usually in a head-to-tail fashion. So you have basically 4 main classes of plant secondary compounds. You have your aromatic shikinic acid derivatives, you've got your aliphatic alkaloids, your acetogens, and your terpenes. I mean, there are other classes of plant secondary compounds. Those are the four biggies. This is just an example of some alkaloids derived from these different sources. These are aliphatic alkaloids, and these are the aromatic alkaloids. Quinidine, which is from the quinine trees and shown an important medicine in treating heart arrhythmias. Tupocurare from curare, that's used in abdominal surgery and others as a muscle relaxant in certain kinds of surgery. They're beta-carbolines, also aromatic alkaloids derived from tryptophan. Alkaloids are one of the largest classes of secondary compounds and also one of the most structurally diverse classes of secondary compounds. And also, because we get so many important medicines from them, drugs both of use and abuse, and the distinction is really in how they're used, alkaloids are one of the classes that have the greatest economic importance for us. One of the things that we get from plants that is most important for our health and well-being. This is a slide I haven't put up before, and I'm not sure how much I want to go into it. I don't know exactly how to say this. It's one of the things that's always struck me as curious about the biosynthesis of these aromatic compounds, these things that branch off the shikimate pathway, is what you might call curious parallelisms in biosynthesis. It's either something important or it's so what, ho hum. I'm not sure which. I think it's kind of neat. You know how sometimes people on DMT or sometimes on mushrooms report having the experience that you can kind of turn the circuit board of reality over and see how it's wired, and you realize that, it's not at all what it appears to be. This is sort of on that level. I don't know if that really makes any sense. This particular slide here shows how these three aromatic amino acids arise. This is your CO2 plus H2O plus Y. Photosynthesis leads eventually to these two simple sugars, which are formed into shikimic acid and then chorismic acid, and out of that, you get your aromatic amino acids branching out here: phenylalanine, tyrosine, and tryptophan. And then also other important metabolites, folic acid, and so on, which we're not really ready to go into. But then if you look at the classes of secondary compounds that come off of each one,
doing on time. Alright, that's not too bad. I'm going to mix up a black real quick and redo the lines, and that should probably finish out this section.
You can get decarboxylation to form the amines, beta-phenethylamine coming from phenylalanine, and tyramine coming from tyrosine. So basically you've removed an acid group and you've left the amine intact. And then from these simple amines, you get things like mescaline, which interestingly enough is the only hallucinogenic phenethylamine in nature, although it's given synthetic chemists such as Sasha Shulgin many ideas for many analogs, but they're not found in nature. You get neurotransmitters such as dopamine, norepinephrine, or epinephrine, and norepinephrine. Ephedrine, another plant compound, that has some of the stimulatory properties of amphetamines. And then even further down the chain, you get complex alkaloids in which these amines, these simple amines, are precursors that are incorporated into more complex rings, morphine, tributylpurine, and so on. The other thing that can happen to these simple aromatic amino acids is instead of losing a carboxyl group, instead of losing an acid group, you can lose the amine. And then you have your phenylacetic acid derivatives. Things like cinnamic acid, caffeic acid. They can lead, these are widespread in coffee and a lot of spices. They contribute to the flavor of coffee, spices, this sort of thing. Things like safrole and nutmeg. Safrole, which is a constituent of nutmeg oil, dill-labiol and dill oil, they're also basic simple derivatives of these cinnamic acid derivatives. They are fragrant. Their biological activity is basically that they're volatile. And then these can further join into dimers. They can form dimers and form a class of compounds called lignans, which are things like protophyllotoxin. It's an anti-cancer drug. There are many interesting ligands, and they have a whole range of biological activities, ranging from some are antimicrobial, some are antiviral, and some have activity on the central nervous system. And then if they polymerize even further, you get lignins, which are polymers of these C6, C3 units. The C6 in the ring and the 3 carbon units sticking out from it. When it becomes polymerized, you get lignin. And lignin is the major structural constituent of wood. Lignin is what gives trees its strength. And interestingly enough, when I was a graduate student at the University of Hawaii, my professor was interested in stress physiology, and he showed that by growing seedlings under conditions of increased gravity, by growing them, he was interested in gravity as a biochemical determinant. And he showed that he would put seedlings in a centrifuge and germinate them there, and show that the levels of lignins were increased. And not only were they increased, if he did anatomy, if he took sections of these seedlings, he showed that the distribution was corresponded with the points of maximum stress in the plant. So this is, lignification. The lignins are deposited on the cell walls. This is basically a gravity-determined property that governs the distribution of these lignins. I mean, if you make an engineering diagram of a tree where the major points of stress are, that will match exactly where the maximum depositions of lignins are. So, whatever. So that's kind of the story with the aromatic amino acids, phenylalanine, and tyrosine, the precursor of the phenethylamines, and the complex alkaloids that come off that. And then this class of compounds, the essential oils, and the lignins, and then the lignin itself. So if you look at the same thing with respect to tryptophan.
Alright, fun. I like that better as the foundation for further glazing. That gives it more character, more definitive form, non-form, abstracted figure kind of thing. And, yeah, so I'm going to finish wiping my hands up before I touch my camera. Ramble a minute. Zoom in and check out that texture. It's pretty cool.
So this is basically a very important plant growth hormone. But it doesn't seem to go, there's not a vast array, unlike with the deamination products.
So that adds a lot of nice translucency, some facture, some light absorption, and some general character to the figure. So we'll let that sit up over the weekend while I'm at garage art, and along with red, and we'll have probably red done next week. And this one, I'm not quite sure how long it's going to take, but some very exciting paintings going on at garage art right now as well. We're working on those tomorrow and Sunday. If anybody needs any art, I am between Allsup's and Outback Pizza, Taos, New Mexico. So that's it for the moment on this. Have a good evening, Earth. That's Adam Sturch broadcasting from the Mushroom Mansion, Taos, New Mexico. Working on oil painting orange. Second in the secondary triptych.
Is basically 2 steps in the